The other day we looked at solving systems by graphing, so we need to look at the other two ways, which are substitution and elimination, which are both ways to solve algebraically. And they do just what they say. For substitution, we substitute in for a variable into another equation. Because remember, with the system, you have to have at least two or more equations with two or more variables. So we solve for one variable and plug it in or substitute in for another. Whereas elimination, we totally eliminate one of the variables, right? Get one variable eliminated. So let's quick talk about when we should use all three of our methods. Well, when should we graph? Basically, the only time we ever want to graph is when our equations are written in slope-intercept form, because then it's nice and easy to work with. And also, we'd probably want to have a graphing calculator as well, because graphing these by hand wouldn't be very exact. So graphing calc and making sure that it's in slope-intercept form. So not very often do we ever want to graph. Solving algebraically, well, when would we want to use substitution rather than elimination? Substitution is easiest when your variable has a coefficient of 1. And what I mean by that is really it has no coefficient. Its coefficient is 1, but it doesn't really show up. I'll show you what I mean. So for example, if I have two equations that say x equals 4y minus 2, and then I have 3x plus 2y equals negative 8. If I look at my first x here, there's no coefficient in front, so really there's an imaginary 1 right there. But we don't see it. We never write that. So in this case, if there's a coefficient of 1 or nothing in front of one of the variables, I would just substitute. I could just take this and plug that in for x in the other equation. That's the best time to substitute. Otherwise, if there are coefficients in all your variables, more than likely you want to use elimination. So elimination is for almost every other time. So every other, like all situations besides these two. So every single situation besides those two. So if it's in slope-intercept form, graph it. If one of the variables has no coefficient on it or a coefficient of 1, substitution. Otherwise, use elimination. So let's go through our examples here just so we can get a feel for what these look like. So if we take a look at that second equation, there's no coefficient on the y, or it has a coefficient of 1 really, right? So we want to use substitution. So I can substitute this x minus 1 in for y, because I'm saying that's what y equals, right? So I can plug it in for y. So I'm going to rewrite this top equation. So 3x minus 4 times, anytime you plug something in for a variable, I always put it in parentheses, so x minus 1 equals 8. All right, our goal is to solve for x, so we need to simplify the left side of this equation. So I'm going to distribute my negative 4 right here. So negative 4 times x is negative 4x, and negative 4 times negative 1 is a positive 4. And don't forget to bring down your 3x, and I still have my equals 8. And let's simplify our two x's, our like terms. So a 3x and a negative 4x give me a negative x, plus 4 equals 8. And let's solve for x, so we get the 4 over there by doing the inverse on minus 4. So negative x equals 4. Well, we don't want to know what negative x is. So the quickest way is just a positive x must equal a negative 4, right? The signs just flip. Realistically, I'm either multiplying or dividing by a negative 1 on both sides. So x equals negative 4. Am I done? Is that my answer? No, if I'm going to solve a system, my final answer needs to be an ordered pair. So I know that x is negative 4, but what is the y? Well, you need to plug your negative 4 into one of the equations. It doesn't matter which one. Just do the easier route. So I'm going to plug it into this second equation. So y equals a negative 4 minus 1, so y equals negative 5. So there is my solution. So all solutions should be an ordered pair just like that. So that's the only point that works for both of these equations. If I were to graph both these equations, that would be the point of intersection. What about this next one? Would it be better for substitution or elimination? You know, you could probably go either route, but substitution would be easier. And because why? Well, this y over here doesn't have a coefficient in front, or really a coefficient of 1. But I still have to get the y by itself. So what I need to do is I need to add the 5 over to the other side to get the y by itself. So really this equation becomes y equals negative 3x plus 5. So I just replaced that equation. Now I can take this negative 3x plus 5 and plug it in for y right there. And it's just the exact same thing. We solve for x. What do we get for x? We plug it back into either equation, and we finish it off. Okay, but just remember, anytime there's no coefficient or really a coefficient of 1 on any variable, substitution is usually the best way to go. Okay, so now if I get an example where all the x's and y's have coefficients, this is where we want to use elimination. And eliminating just means let's get rid of either the x's or the y's. And to do that, we add or subtract the two equations together. I always add them, and I'll tell you why here in just a second. So if I look at these two equations, first I decide, should I eliminate the x's or eliminate the y's? Well, if you notice, here's a positive 2x and a negative 2x. So what would happen if I added those two guys together? Yeah, they would eliminate each other, right? A positive 2 plus a negative 2 give me 0. That eliminates it. So what I'm going to do is I'm going to add these two equations together so I can eliminate those x's. So that's my goal. I always want to get a positive variable, and I want to get its opposite right below it so they eliminate when I add. That's my goal. So here, 2x plus a negative 2x, that's gone. They eliminate each other. Negative 3y plus a 5y gives me 2y. And then 12 plus 10 gives me 22. And then I solve for y by dividing by 2, so y equals 11. And like we said before, our all answers need to be an ordered pair. So I know the y is 11, but to solve for x, I have to go plug that into one of the two equations. So I'm going to go ahead and plug it in to this guy. So let's rewrite that. So I got negative 2x plus 5 times 11 equals 10. So negative 2x plus 55 equals 10. Let's get our x by itself. So we subtract 55 from both sides. So negative 2x, that's gone, equals negative 45. And divide by negative 2. So x would give us 22.5 or 22.5. So there we go, 22.5 and 11. So it's nice and easy when they give me the x's lined up and they're opposites of each other. But what happens when that's not the case? Well, we got negative 4x plus 15y equals 8, and then 6x equals negative 5 plus 5y. Well, if we notice, when the x's and y's are lined up like the last example, it's much easier. So that's the first thing I'm going to do. I'm going to get the x's and y's lined up. So I'm going to rewrite this top equation. I got negative 4x plus 15y equals 8. That's nice. But I want to move this y over to the other side. So I need to subtract 5y. Subtract 5y. So now I can rewrite that as 6x minus 5y equals negative 5. Well, now I have to decide, should I eliminate the x's or eliminate the y's? Well, the easiest thing to do is to decide, how is it going to be easy to get opposites? Well, if I look at the x's, negative 4x and a 6x, if I wanted to get those to be opposites, I'd have to think of the least common multiple between the two to get them to. So if I think 6 and 4, I could get them both to 24, but I could also get them both to 12. So if I could get this negative 4x to a negative 12 and the 6x to a 12x, I'd be good. So I'd have to multiply both the equations by 2, right? I'd have to multiply this top equation by 2 and this bottom equation by 2. Okay, before I do that, would it be better to eliminate the y's? Yes, I think so. Because why? Well, I wouldn't have to multiply both equations. I'd only have to multiply the bottom equation. Because this is already a 15y, so let's get this guy to a negative 15y. Well, how do I do that? I'd have to, algebraically, whatever I do to one side of the equal sign, I have to do to the other. So if I multiply by 3 to get this negative 5y to a negative 15y, I have to do the left side by 3 and the right side by 3. So I'm going to replace that equation. So I got 3 times 6x, which is 18x. And then I got 3 times negative 5y, which is negative 15y, equals negative 5 times 3, which is negative 15. And I'm going to bring down my other equation. So I got negative 4x plus 15y equals 8. Okay, so I'm done using these guys. Now I have opposites, right? I got a 15y and a negative 15y, so I can add these two equations together. So they eliminate each other. And then we just add. Negative 4 plus 18 is 14x equals, well, 8 and negative 15 gives me negative 7, and divide by 14. So x equals negative 1/2. Okay, so far so good. So that's part of my solution. Negative 1/2 for x. How do I find the y? We'll plug that in. Well, I could plug it into any equation that I want. Which one would be the easiest one to plug into? I'm going to plug it in way back over here into that x. I could have plugged it in into this x. I could have plugged it in into that x. It doesn't matter, wherever you want. So I'm going to go back to this very first one. So 6 times negative 1/2 equals negative 5 plus 5y. Well, half of 6 is 3. Positive times a negative is a negative. And now let's go ahead and solve for y. So the opposite of a negative 5 is a plus 5. Do that to both sides. We got 2 equals 5y. And divide by 5. So y equals 2/5. So I got to put that back over here. So there's my final answer. Remember, they're all ordered pairs. Negative 1/2 and 2/5. So just be careful. Depending on how the equations are written, either graphing will be easier, or substitution will be easier, or elimination. So just be careful.